Okay, today we compute various potential energy. The potential energy exists for any conservative force. If it is a conservative, then the integral of work is always vanishing when you follow a path, closed path. Then it is always vanishing. So use this definition to find the potential energy. And in here, we have a reference point. This reference point and its value of the potential energy is free to choose. It is arbitrary. It does not contribute to the force because if we take the minus gradient, then this constant term always disappear. So when you compute the potential energy, you need to integrate over a path from a reference point. And the integral can be done in very, very many ways. So among them, you had better to choose a simplest path because we have a freedom to choose the path. For example, from here to there, sometimes it's better to choose this path, and sometimes it is better. And in general, you can choose this path or any path because of the path independence of the integral. Once you know the potential energy, you take the derivative minus the gradient, attach minus the gradient to the potential energy to obtain the force. This is an example, simplistic example of the gradient of a single Cartesian coordinate. If it is x coordinate, this derivative disappears and only this one survives, and that is a trivial derivative, that is 1. Therefore, this one gives coordinate x1 gradient is just nothing but a unit vector along the x-axis, unit vector along the y-axis, and unit vector along the z-axis. This gradient operator also appears as a scalar product. In that case, 1, 1, 2, 2, 3, 3 components will be combined together to find the x components x derivative, y components y derivative, z components z derivative, and sum them all. That is divergence. Suppose that a vector A is a constant, then we find x1 a1, x2 a2, x3 a3, whatever, they are all vanishing. I equals 0. 4i equals 1, 2, and 3, because this is constant. In that case, we make use of these formulas. Gradient of each coordinate is just a unit vector along that Cartesian axis. Therefore, x dot A is x1, a1, x2, a2, x3, a3, but this one all disappears, and these are all unit vectors, e1 hat, e2 hat, and e3 hat. Therefore, the result is just a vector itself. This is a very useful formula. In the previous class, we learned that if curl of f is 0, there exists gradient u that satisfies the force. That means the potential energy exists. This is the very strong condition of the conservative force. If F is constant, well, we just make use of this simple formula, x dot A, when A is a constant vector. X dot A gradient is just exactly A. Therefore, if F is a constant force, just like a constant gravitational force, this is constant always. In that case, what we can do is just, this is identical to F dot X gradient. Now, I attach negative sign on it and F dot X, right? In that case, I have a force expressed in terms of minus a gradient something. So this is the potential energy. However, I can always add any arbitrary constant without changing the force. Number 4, this is a simple application. F is a constant. Gravitational force, constant gravitational force is constant. So what we can do is just substitute this F with mg, and the final result is obtained as a usual form. Find the false statement regarding the gravitational Wi-Fi. That's fine. So we have seen this problem many times. Now we can deal with this problem with the conservative force. Once you know the potential energy must depend on the position only. And if we choose u of x to be 0 at D, okay, reference point, if we have a freedom to choose the reference point, now we have chosen this one as a reference point. The height is r, so C and A has mgr. What we can use is this formula we just have derived. And if we choose B to be the reference point, if U is 0, these points are lower than this. So if we choose U to be 0 in here, then these points is below B by R. So we have minus mgr. And what about here, dA? This is minus 2mgr, right? Electrostatic force, this appears in the next semester. Or if we have a parallel plate capacitor, with the charge sigma and minus sigma, where sigma is the charge divided by area, something like that. The electric field is uniform constructed between the two plates from the positive charge to the negative charge. In this case too, we simply make use of the formula. This is a very useful formula. Any constant vector can be expressed as x dot A gradient. So use this identity to find the potential energy for the electrostatic case too. Number 7, we have a pivot and we have a lever arm of length L, and we have an angle theta, either this theta or that theta from the vertical line. If we choose the reference point to be in here and choose the reference value to be u0, then this is above this reference point by L cosine theta. right? So it is below the reference point by cosine, L cosine theta. So if we choose the reference point to be here and its value is u0, then it is u0 plus mgl cosine theta. And here we have negative sign on it. Now we apply the method to compute the potential energy for the restoring force, satisfying Hooke's law. This is a scalar. X squared is x1 squared plus y2 squared and the z other x2 squared and x3 squared. It can be written xyz, something like that. Anyway, this one gives the first term. This one collects the second term only, and this one collects the third term only, and they are 2 times something, right? 2 times x1, 2 times x2, 2 times x3. So if we multiply this one by these unit vectors, what you can get is just x vector multiplied by 2. So gradient of x squared is simply 2 times x. Therefore, x vector is just 1/2 of a gradient of x squared. Now we can replace this one. This is a minus kx, but that is a 1/2 gradient x squared. Now this is a force, and force should be written in the form minus gradient potential energy. Therefore, the potential energy, this potential energy, is 1/2 kx squared, and I always have a freedom to choose the constant c, but simplest choice is just to kill this. This c can be chosen to be 0. All right. This is the inverse square law, right? 1 over r squared, and this k is a constant, whatever. Sometimes it is 1 over 4 pi epsilon 0. In that case, it is the electrostatic force multiplied by charge Q1, Q2. If we have G, capital G, and mass M1 and M2, then what happens? This is just for gravity, right? Newton's universal gravity formula. So whatever, we just put this k to be a constant. Sometimes I can make use of this. Sometimes I can make use of either case. I can just choose k to be a constant, and later I can substitute some value. And we have a unit radial vector. This is a 3-dimensional unit radial vector. That means x1, e1, x2, e2, x3, e3, divided by square root x1 squared, x2 squared, x3 squared. That is radius r. Because this is a unit vector, magnitude is 1. The force, magnitude of force is just a constant k over r squared. So it decreases as radius increases by r squared. So we say it is inverse square law. Now let us compute the gradient of r. R is square root x squared, y squared, z squared. And in the previous class, we have done a lot. And we can make use of chain rule. Square root of something's derivative is 2 times the square root, right? And then we take the derivative of this one, x1 squared, x2 squared, x3 squared, with respect to x1, x2, and x3, right? So the final result is this is 2 times x1, 2 times x2, 2 times x3 multiplied by unit vector, so that is 2 times vector x. And this factor 2 cancels the factor 2 in the denominator. Finally, we end up with the vector x divided by its own magnitude, so it is unit radial vector. You have noticed that any coordinates gradient, any coordinate, for example, x1's gradient, that is the unit vector along the x-axis. Gradient of y, that is y-axis unit vector. Gradient of x-axis, this is z, then this is a z-axis unit vector. And gradient of r, that is unit radial vector. Very simple. And then for any n, even for the real number, we have derivative is just n times r to the n minus 1. It is also true for 1 over r, for r is not equal to 0. In that case, it is 1 over r squared. Now, let us compute the gradient of 1 over r. Gradient of 1 over r can be computed by making use of chain rule. First, we take the derivative of 1 over r with respect to r, and then take the gradient of r, that is the chain rule. And we know everything already because the first order derivative of 1 over r is in here, minus 1 over r squared. And then what is the gradient of r? That is unit vector along the unit radial vector. So just to copy those results in here, I have found that the gradient of 1 over r is 1 over r squared, and its opposite direction to the unit radial vector. The reason is that 1 over r decays. As r increases, this 1 over r decreases. And you know, the gradient is the direction of increasing. So gradient is toward these higher positions, right? That's the reason why unit radial vector is this direction. Gradient is toward the center. Finally, this force satisfying the inverse square law can be expressed as a minus the gradient of something. And that something is the potential energy. Okay? Now, this one is, this curve is 0. And we know what the potential energy is. This is potential energy. U of x exists. Potential energy exists, then we can make use of the total mechanical energy conservation because it is conservative force. So it is conservative. That means total mechanical energy, that is 1/2 mv squared, sum of 1/2 mv squared, the 1/2 kx squared, that is potential. This sum, that is the total mechanical energy, must be conserved. Must be conserved. That means I can make use of the value at a certain time, and I can keep using that value. In here, at x equals to 0, it has this kind of, here, velocity was like that when x equals a, and the particle stops This one is easier. Stops at x equals something. You know, we have 1, 1, 1, this magnitude of the square root to 3, and divided by square root to 3. So this is a unit vector. This is a unit vector. So magnitude of x is just 2 times a. And at this point, it stops. That means the kinetic energy disappears. So what is the total mechanical energy at this point? So just substitute this value. So 1/2 k 2a squared. That is 2ka squared. That is the total mechanical energy of the system. I can make use of this value at any time. Okay? It should be this, right? This was wrong. Consider a particle with mass m. Mass m is at here, and at C, near point P, and it is a z-axis that penetrate the center of the circular uniform distribution of mass capital M. Okay, this red curve is a circle. This is a circle, and it has a mass capital M, and this circle has the center at the origin. And the radius of this circle is capital R. And distance from this point mass small m to the center is z. Okay. So this is these are fixed points. Superposition principle can be applied to compute the potential energy of a system of massive particles. That means, for example, this part, I can collect all of the components of the potential energy all together. But I noticed that every point on this circle has the distance from this point P. What is this? We have a radius that is perpendicular to the z-axis, and this is a z. And what is the distance, the direct distance from this point to there? That is square root z squared plus r squared. Understood? This is a right triangle. Right triangle. Everywhere has the distance from each massive object. Let me call it the dm, for example. And this one has the distance. That's square root of z squared plus r squared. And we know the potential energy. We have just derived the potential energy of gravitational force, that is inverse scale law, and K is nothing but the G times mass product. So this point mass and this distribution of mass everywhere has the distance this. Therefore, the potential energy is simply this. We could have carried out integration, but that integration is just a trivial integral of whose integrand is just a constant 1 over square root z squared plus r squared. So this is the answer. Trivial. Next, why don't we take the derivative with respect to z? We know how to take the derivative. This is a power, has the power minus 1/2. If I take the derivative, then this factor minus 1/2 appears in front, and then it has been decreased by 1. And then I apply chain rule. we take the derivative with respect to z of the argument that is z squared plus r squared. And if I take the derivative, what I find is just 2 times z, and these 2 cancels in the 2 in the denominator, and I end up with this formula. Except for z, we can notice x and y independent. This formula does not have any x and y. Therefore, if I compute the force, I just apply the minus gradient, and in this minus gradient, I have a minus E1 x derivative, E2 y derivative, and E3 z derivative. However, these 2 contributions disappear exactly because this potential energy does not have any x and y. Therefore, I can make use of this formula only to find that the gravitational forces along this direction. However, this is just a gradient, and minus gradient is a different sign. Next, what we can compute is, this is identical, but let us look at the final result in here. This is the potential energy previously obtained. Why don't we take expansion when r is much greater than z? In that case, I can factor this r out. That is GMM, and I can pull this r out. In that case, I have a square root 1 plus z over r squared. Now, we can apply binomial theorem. We remember this is 1 plus squared, and what is the power? Minus 1/2. If it is a very small, z over r goes to 0, then what I can find is 1 minus 1/2 z over r squared, and the next term is minus 1/2 minus 1/2 minus 1, 2 factorial z over r to the 4th power, and so on. As you have noticed, this is small, so square 4th power, we can't neglect this one if it is very small. So in that case, I can make an approximation when z is much smaller than the radius r, then we can make this approximation. And using this, I can find the gravitational force in this approximation directly by taking the derivative with respect to z. Next, we consider this integral. This is just the training of integration, and we will find that this integral is very, very useful to find what? Newton's shell theorem. Let me first tell you the final result. Newton's shell theorem states that if there is a spherically symmetric mass distribution then you know how to compute the gravitational force between two point masses, capital M and small m. Then the gravitational forces R squared GMM, and they are attractive. However, if it is a sphere, for example, Sun and Earth, how can I compute the gravitational force between them? Simply, I can choose the center of the spherical massive object that has a spherically symmetric mass distribution. For example, if it is a uniform mass distribution inside the sphere, in that case, what I need to do is just point the center and let all of the mass to be placed at a single point. And the gravitational force can be computed by just point mass, and the distance is counted by the distance between the two centers. It is a non-trivial problem, and in order to solve this problem, Newton invented integration. And this is not exactly the same version, but this version is a much simpler than Newton derived originally. So we begin with this integral. It looks complicated, but we have, this is C. This is a single variable. So if I want to compute this integral, what I need to do is to carry out this integral. This one can be done by taking the derivative. If you take the derivative, you will find the integrand of this. Therefore, this is trivial. Now we can change the variable. I can multiply some positive number. Either it can be positive or negative. Anyway, the inside the square root, the whole thing must be positive definite. It cannot be negative. So by changing variable, we can derive this integral directly from this integral table. And then next step, this A is this B is replaced with R times Z. Now, this is the final form, and you will find what A and B are, and just substitute these values into here to find out the integral table, like that. This integral table is very, very useful. Now, this is a primitive function for this indefinite integral, and what we have to do is to carry out these definite integrals. Definite integral is to substitute those values. For example, I substitute C equals 1 in here. What I find is R squared minus 1 minus 2 R Z plus Z squared. Oh, it's nothing but R minus Z is squared. And I need to take the square root. What it is? You know, this is R minus the absolute value. If I substitute minus 1, what I would get is just to replace this negative sign with a positive sign. Because there is a negative sign in front of it, our final result is this integral looks very complicated, but the final result is trivial. Absolute value of R plus Z minus absolute value of R minus Z. divided by RZ. Sometimes we need to evaluate this integral with the upper limit is replaced with the 0. If we substitute 0, what I get is r squared plus z squared. The linear term disappears. Now, let us make use of this integral table to evaluate this. This is a sphere, just a hemisphere. The full sphere have been cut into two pieces, and I have removed a single hemisphere, and I end up with a single hemisphere with radius capital R. What I would like to do is to compute the potential energy between the two, this point mass M and capital M distributed uniformly over this sphere, the hemisphere. Now we have to do some integral. Let's see. Its mass, this capital M, is distributed over the hemisphere. The surface of the sphere is 4 pi r squared, and this hemisphere has a surface 2 pi r squared. And I assume this mass is distributed uniformly over the hemisphere. And then what I have to do is to consider the area element. That area element is, if I choose the angle theta in here, and let me vary this position. So this is a kind of annular region, just like a ring we have already computed. And what is this area? If I choose this to be theta, for example, this z-axis r and theta, and z component is just r cosine theta, and this is a right angle. This perpendicular distance, this is the perpendicular distance, that is r sine theta. So the circumference of this is, because this radius is r sine theta, this circumference is 2 pi r sine theta. Okay? And what is the width of this? That width is just, because it is a circle, and we have angle theta varies, this is a theta, and let me call it this d theta, and this is a circle of radius r. Therefore, this width is r times d theta. Therefore, r times d theta is the width, and the length, this circumference is 2 pi r sine theta. If I multiply, then what I get for the area is 2 pi r squared sine theta d theta. So, and actually this sine theta d theta can always be replaced with the d cosine theta. This total differential is much easier when we compute the integral. Therefore, I can substitute all these results combined. The potential energy is simplified in this kind of form, where theta is the angle I have just shown. Then we end up with this kind of integral that we already derived. The integral table is derived in here. Aha, this is for the hemisphere. that we are right now considering. Hemisphere, we have this strange term appears. And why don't we extend this idea to cover a whole range of the spherical surface? Let us compute that. So this is just simple algebra. I won't explain. It is just you can just follow everything in here because solution is completely given. Simply, this is after considering all possible cases, you will find that absolute value of a plus b minus absolute value of a minus b divided by ab is 2 times 2 over maximum value of a and absolute value of b. It is a very interesting math formula. Using this, we can compute the potential energy between this spherical shell. Shell means it is just a crust. It is empty inside. It has just the surface in it. And inside the surface, it is empty. So mass m is distributed over the spherical surface only. In that case, we can carry out the same integration. What we have to do is just to replace this upper bound. Previously, upper bound was 0, but this cosine theta extends from -1 to +1. Therefore, this upper limit has been replaced with 1, and lower limit is -1. And we just make use of the integral table, and then we have r plus z minus r minus z over rz. And this arithmetic formula gives just 2 over product of the maximum value of a and absolute value of b. We know a is r and z can be negative. So that's the reason why I have to compare this radius capital R and absolute value of coordinate z. Coordinate z is the position of this point mass. Finally, the result shows that it is trivial. GMM is a gravitational constant and the product of two masses, and a very striking result. Potential energy is 1 over z absolute value. Z is what is z? From the center of the sphere to the point mass. This is the absolute value of z. When z is greater than the radius, then it is 1 over z. Okay, we have a sphere, distance z, absolute value. Potential energy is minus gmm over z, the distance between the point mass and the center of the sphere. Okay, and then what happened next? Potential energy in here is 1 over r. There is no z dependence. When this object penetrates the surface, and if it is placed inside the sphere, what happens? Potential energy is a constant. R is a constant. That means there is, if you take the gradient, it is vanishing. It is a 0, absolutely 0. So inside a sphere, this point mass does not feel any gravitational force. That is the remarkable result first obtained by Newton. And this is a shell theorem. Okay? Next, we considered case when the sphere is filled with mass. So now we consider mass density is distributed over the whole space inside the spherical surface. In that case, so what we have to do is additional integral that is a radial integral that is again trivial. And the solution is completely given in here. We discussed the final result. That is, if the sphere is filled with mass, then at the center it does not feel any gravitational force. And if it is a spherical surface, then inside there is no gravitational force. However, if it is filled, then this point mass fills the mass inside this radius. And if you approach the center, the mass inside the spherical surface becomes tiny and smaller. If you approach it at the center, there is nothing inside. Therefore, at the center, this point mass does not feel any gravitational force at the center. And if you depart from the center, we have a radius small r that is smaller than the capital R of the radius of the original sphere. Only the contribution of this small sphere contribute to the gravitational force. That's the reason why we have the gravitational force of 1 over r squared dependence, but mass inside the small radius r is proportional to r cubed. This r squared cancels, and the remaining piece has the dependence of r that is linearly increasing. And when it approaches the surface, it feels the whole amount of mass inside the sphere. So at the border, just on the spherical surface, just like we on Earth, we feel this, and this is mg, and small g is the gravitational constant and mass of the Earth, and our mass divided by the radius of the Earth. This is Newton's shear theorem. So that's it for today.